Hi students, welcome to example exercise 27A, application of exponential functions. And we're specifically going to be talking about problems that involves interest today. Okay, so recall the exponential function. So it can be written many different ways, but basically here we have all the different transformations where A is your vertical stretch, B is your horizontal stretch compression, obviously, C is your base, x minus h, this is your horizontal translation, and your vertical translation. Okay, specifically compound interest, so to be very general, the way the bank works with money is represented with this equation. Okay, so A is the final amount, so A is whatever you have at the end. P is the initial amount, so the amount you invest. R is your interest rate as a decimal, so for example 5% would be written as 0.05. N is the number of compounding periods in 1 year. And I'm sure we'll talk about this more in class, but compounding periods is the amount of times that the bank will give you interest on that money. And T in time is in years. Okay? So, let's go with the first example here. Cal invests $1,000 at a 3.5% compounded annually, which means if it's compounded annually, only once will the bank give you any return or any interest on that value. Okay, so write an exponential function to model the growth of Cal's investment. So, A is the final amount, so that's the number we will not know. P is the amount you've invested, so that's the $1,000. So notice that's your your stretch. 1 plus R, which is 0.0375, right? Because it's 3.75%, you turn it into decimal, so move the decimal twice over. 1, 2, over, compounded annually, therefore we're only going to get that return once, and n is 1, so you have 1 times t, which is don't know, so we're going to write t. So it would really depend on the amount of years that you leave that money in. Okay, determine the value of the investment after 7 years. Well, that's simple. We've just stated that t is equal to 7, right? And so A equals to 1,000. Notice that because this is over 1, it's 1 plus this. So inside your bracket, you're just going to have 1.0375 to the power of 7. Okay, and this is definitely something where you need to use your calculator. So you plug that into your calculator. Notice that you have to put in every decimal there, so don't stop at 1.03. Precision is very important in this unit because of the exponential functions. And you put it to the power of 7, you get $1,293, 93, not 99. So 93. And since we're talking about dollars, I'm going to stop at the decimal of the hundredths, and dollars here. I'll put dollars in front. Okay, so you get $1,293.95. All right, next question. How long would it take the investment to triple in value? So if I know that my original investment is 1,000, the triple of that will be 3,000. So I'm asking how long is it going to take for my final investment, or the final value, to be 3,000? And none of this changes, and I'm looking for solving for time here this time. Okay, well, first thing I'm going to do is divide by 1,000. Notice that t is in our exponent. That is the variable in the exponent. So this is going back to exercise 25, where we're solving equations where x is in the variable, or in the exponent. So first thing I'm going to do is I'm going to divide by 1,000, just to get rid of this 1,000 over here. So let's divide by 1,000. Okay, what we're going to get is 3 equals to 1.0375 to the power of t. I'll leave that in brackets because it's a big number. Okay, if you recall, to solve an equation with a variable in the exponent, when the bases are different, you'll need to use logarithms. So what I'm going to do is I'm going to take the log of both sides. So what that looks like is you get log of 3 equals to log of 1.0375 to the power of t. Okay, and I'm going to continue up here. So now what we're going to do is we're going to drop this exponent right in front of the log. So what we're going to get is log 3 equals to t log 1.0375. Okay, and now I can solve for log just by dividing by log of 1.0375 on both sides. So do that same on both sides. 0.0375. Okay, so that's going to cancel out this log of 1.305. And what we have left at the end, we have log 3 divided by log 1.0375 equals to t. Okay, so again, your calculator, you plug that in. Make sure you're using the proper brackets. Probably a good idea to practice to make sure that you get your total. And what we get is 29.842 equals t. So those would be years. Okay, so therefore, it would take 29.842 years to triple in value. Okay. Okay, so there are also formulas that help you work with deposits when, instead of making one lump sum, like one big chunk of money, let's say you make investments every month. So let's say you invest $1,000 or $100 every month. So this is what this would look like. So again, just give it a formula with different variables. So FV is the future value. Okay, so that'd be your final value, future value. R is the regular investment. So again, just stating different variables. You need to be able to deal with different equations at different times. I is the interest per compounding period. So a little different here. Here if it's compounded monthly, right? If it's 9% compounded monthly, you would say, okay, well, there's 12 months in a year, so you would divide that 0.09 by 12, which is 0.0075. So this would be your value of I, okay? And N is the number of investments. Okay, so let's say we invest $100 each month and an annual interest rate of 3% compounded monthly. How many investments are necessary for investment to grow to $40,000? Okay, well, again, I'm just going to use this formula, pretty straightforward. I'm looking for the future value of $40,000, so that's a given value in the formula. So you have $40,000 equals to R, which is $100, which is our investment per month. And then bracket 1 plus I. Well, I is 3%, right? But it's compounded monthly. So our I, I'll just write it off to the side here, would be 0.03 divided by 12. And what you get from that is 0.0025. So it's 1 plus 0.0025 to the power of n. N is something I don't know. So that is the variable we're going to try to solve. Oops. So n. And then minus 1. And all that is divided by I, which is our 0.0025. Okay, so really the purpose of this question is to solve for n. First thing we're going to do, we're going to isolate this exponential function as much as possible, which means I need to bring this over to the other side, I need to bring this over to the other side, and I need to bring this over to the other side. Okay, so first step, I'm going to multiply by 0.0025 on each side. Okay, so there's more than one way to solve this, but I think this would be the most straightforward way to do it and explain it. So I'm going to multiply this by 0.0025. Okay, so that's going to cancel that out, right? So again, you're going to have your calculator for these types of questions just because of the nature of these numbers. So then what we get is we get 100 equals to 100 bracket 1 plus 0.0025. Maybe I'll simplify that next time. Minus 1. Okay, again, divide by 100 each side. So divide by 100 each side. I want to isolate for n here still. So divide by 100, divide by 100. Okay, so what we get is 1 equals to, And really, all I have left with is this bracket on the side here. So I'm going to not write those big brackets. I have 1.0025 to the power of n minus 1. So notice 1 plus 0.0025, I just combine that. Okay, so I'm going to bring this 1 over, so that's just plus 1 on each side. I don't think I need to write that one. And we've isolated our exponential function completely. At this point in time, again, our variable is in the exponent. We're going to use a logarithms, so we're going to apply logs on both sides. So we have log of 1.0025 to the power of n. Our n can now drop to the front, so now I have log 2 equals to n log 1.0025. So this question looks very similar to the other one at this point. You divide by log of 1.0025 on this side, and what you have left is log 2 divided by log of 1.0025 equals n. So that will be the amount of investments necessary. So you go log 2 divided by log 1.0025 in your calculator, and you get n equals to 277.605. Okay, well, you have to understand this a little bit too. Okay, at 277 investments, we will not have $40,000. At 278, we will have at least $40,000. So therefore, in any case here, even if it was 0.1, you'd have to round up to the next investment. So therefore, it takes 278 investments to get $40,000. Okay? All right, in this last case, so again, a different equation. This would be an equation where you're paying down a loan or a mortgage. So when you borrow money from the bank, okay, and you're paying down a mortgage, so eventually you own your house, for example. Okay, so this is a decreasing function since the debt is constantly getting smaller. So let's say you borrow, for example, using our example, $250,000 to buy your house. Well, as you pay down your mortgage throughout the years, that number gets smaller. So this is a decreasing function. Notice that this is a negative exponent, so that's a description of a decreasing function. Okay, so let's go over this equation. So PV, the present value of the loan, so that's how much you still owe. If you borrow $250,000, that's your present value of the loan. Your regular payments, so your monthly payments on your mortgage or against your loan, whatever that is. Interest per compounding period, so that's very similar to the last example, where if you have 9% interest rate but it's compounded monthly, your monthly interest would be 0.0075, and n is the amount of payments that are necessary to repay the loan. Okay, so let's look at the example. Very common in today's world. You borrow a mortgage of $250,000. That's pretty, if anything, that would be a lower priced home in these days. And the annual interest rate, the annual interest rate is 2.5% compounded monthly. Okay, so be careful. This is 2.5% annually, but it's compounded monthly. So you need to divide that by 12 to get that I rate, right? Okay, so we can only afford to make a monthly payment of $1,200. How many payments are necessary to pay our debt? How many years did that take? Okay, well, let's first find out how many payments we need to make if our monthly payment is only $1,200. So our future value, our present value of our loan is $250,000. Our payments are $1,200. Okay, and then you have 1 minus 1 plus I, and again, I is 0.025. That's our yearly divided by 12 because it's a monthly compound interest. So 0.025 divided by 12. Okay, so here we don't have an exact value because if you guys look in your calculator, you've got a decimal value that continues to infinity. So I'm gonna use this value specifically like that because that is an exact value. Okay, so we're gonna have 0.025, divided by 12. All that is to the power of negative n. N is the amount of payments, and that's what I'm looking for. And all that is divided by our I value, which is 0.025 divided by 12. Okay, well, just like we did in the last example, I want to solve and isolate this exponential function because that's where the variable exists. So I'm going to move this over here, I'm going to move this over here, I'm going to move that over here, and then we're going to be able to solve for that using logs. Okay, so the first thing I'm going to do, okay, so multiply each side by 0.025 divided by 12, right? That's going to cancel that out. And I'm going to do the same thing on this side, obviously. And hopefully we get something that's pretty good. So we multiply that by 250,000. Okay, and we get 520 0.83 to infinity. So I'll put that down. When I plug that into the calculator, I'm going to keep all the decimals as possible. So that's 1200, 1 minus 1 plus 0.025, 25 divided by 12 to the power of negative n. Again, all I'm doing is solving for the exponential function. I'm going to divide by 1200 on each side, right, to get rid of that 1200 over here. Divided by 1200. Okay, so I'm going to try to keep as many decimals in my calculator as possible. If you guys want to leave it as a fraction, feel free to do so. So 43027, actually it's probably 7 to infinity here. Just to stay as consistent as possible with my calculator, I'm going to keep all the decimals and stop there. 1 minus 1 plus 0.025. Divided by 12 to the power of negative n. Okay, so now I'm going to subtract 1 on each side, right? Because this is a positive 1 here. So I'm going to subtract 1 on each side. Okay, what we have left is negative 0.565972222 equals to negative 1.025 divided by 12 to the power of negative n. Alright, so now I divide by negative each side. Okay, so basically I just turn both sides into a positive value, and then we're going to be ready to use our logarithms. Oops, it's not a z. Equals 1.0.025 divided by 12, all to the power of negative n. Alright, so now, like I said, we've completely isolated this exponential function. So now we can use logs to drop this exponent down. So I'm going to use log on both sides. So I have log of 0. All this stuff here equals to log of this to the power of negative n. And recall, whenever you have an exponent of an argument, that exponent can come down. So then you have, I'm going to go down the page a little bit, 1.565972222. So I'm missing a 2 there, I think. Equals to negative n log of 1.0.025 divided by 12. Okay, so as I did last time, I'm going to divide each side by the log of this. Okay, I'm going to divide that over here to isolate n. Notice that n is negative, so I'm going to have to change the sign on the other side too. So one last one. I'm not going to write all this stuff again. I think we're ready to get a value here. So that's your numerator divided by log of that. Okay, you've got your calculator. Take that out. Make sure that you can get the values that I'm going to give you right now. And we get negative, sorry, I'm going to write equals negative n. We're going to get negative 273.505 equals to negative n. And therefore, whoops, don't want to do that. And therefore, n is equal to 273.505 positive, right? Because both sides are negative. All right, so again, to pay off your mortgage, the last payment, if you notice, will not be a full payment, right? It'll be closer to a half payment. So you'll have 273 payments of $1,200, and then your last payment will be probably about half of that. So we also wanted to know how long that would take. Okay, so let's go say therefore 274 payments. Well, if you think about it, you make a payment per month, right? So to find the amount of time it's going to take you, you just got to go 274 divided by 12, and that'll give you the amount of years and months necessary. So 274 divided by 12. Okay, so that's 23. So that's equal to 22 and 10 months. So 22 and 10 twelfths. So that's equal to 22 and 10 twelfths, which means it's going to take you 22 years and 10 months to pay off your mortgage. All right, guys. Every equation is a little bit different, but I'm going to present them to you in the questions. Good luck, and you obviously have these three to work with.